Welcome to a tutorial for the paper Adjusting for Publication Bias in JASP, Selection Models and Robust Bayesian Meta-Analysis. Today I will explain how to conduct publication bias adjusted meta-analysis using Robust Bayesian Meta-Analysis, short ROBMA, in JASP. ROBMA is a method to correct for publication bias that applies different models simultaneously, some assuming publication bias and some assuming no publication bias. Then it model averages over the different models by giving more weight to models that are better supported by the data for the effect size estimation. More information on ROBMA can be found here in the paper. Now let us open JASP. Here we can see data from LOUI 2015. The reference for the data can be found below the video. LOUI 2015 investigated how the acculturation mismatch of US immigrants from collectivist cultures leads to intergenerational cultural conflict. We will now check whether their results hold up after adjusting for publication bias. To do so, we first click the plus sign in the upper right corner. Then we select Meta-Analysis. Now we can see the Meta-Analysis module appear at the top. Here we select Robust Bayesian Meta-Analysis. First, let us take a look at the input panel on the left side. We can see that we can conduct a meta-analysis based on Cohen's d or t statistics, together with sample size or standard error. This is usually the preferred option because it has highest precision, since it internally uses t statistics. We can also use correlations and sample size, odds ratio and confidence intervals, effect sizes and standard errors, and we can load a fitted model from R. Here we prefer to use correlations and sample size because that's the data that we have available. Before running the analysis, we should check the prior distributions. To do so, we tap Models and then Plot Priors. Now we can check all priors on the right side. First, let us take a look at the model priors. We can see the prior probabilities for an effect are 50%, for heterogeneity is 50%, and for publication bias is 50%. We can also see that 6 of 12 models assume an effect, 6 of 12 models assume heterogeneity, and 8 of the 12 models used assume publication bias. We can also take a look at the probability of each individual model. And here we can see the models described. So for example, spike 0, spike 1 means no effect, no heterogeneity, no publication bias. And this model has a prior probability of 12.5%. However, let us now look at the plots for the prior distributions. First, for the hypothesis assuming no effect, we just have spike 0, so we just assume the effect is exactly 0. For the alternative, assuming an effect, we have a normal distribution with mean 0 and standard deviation 1. However, a normal distribution on the Cohen's d scale, that is shown here, transformed to the correlation scale. This is why it doesn't look perfectly normally distributed, because it's only normal on the Cohen's d scale. For the heterogeneity, we again use a spike at 0 under the null hypothesis. And under the alternative, we use the inverse gamma distribution, which is based on empirical heterogeneities. For the weight function under the null, we just assume all papers are published and there's no publication bias, so it's just always 1. Under the alternative, we have 2 models. First, the cumulative sum of the Dirichlet distribution with parameters 1, 1, which basically assumes that significant studies are always published and non-significant ones half of the time. And then the cumulative sum of the Dirichlet distributions with 3 parameters, which assumes significant studies are always published, and then also differentiates between marginal significant studies that are published 66% of the time, and non-significant studies are published 33% of the time. After inspecting the parameter and the model priors in this way, we can start fitting the models. To do so, we drag sample size to the sample size box and effect size to the effect size box. Now a progress bar will appear at the top. While we wait for the models to fit, we can go for a coffee. After going for a long coffee, we can look at our results. First, let us take a look at the summary. Here we can see the posterior probability for an effect, heterogeneity and publication bias, and also the inclusion base factor. First, let us look at the posterior probability. This tells us that we are now basically certain that there's an effect in heterogeneity because it's 1, or actually slightly smaller than 1, but almost 1. But we don't really know about publication bias. It's only a little bit more likely than before seeing the data. Regarding the inclusion base factor, the inclusion base factor is a continuous measure for the strength of evidence for models, and basically the inclusion base factor for an effect is 2787.678, which is very high. So usually inclusion base factors above 10 are considered strong evidence, so this is very strong evidence, which also is the reason for the high posterior probability. And also the inclusion base factor for heterogeneity is very high. However, for publication bias, we are not really sure, like it's around 1, so we didn't really learn so much from the data about publication bias. We also see a warning message. However, this is harmless and just says that the models failed to fit due to incompatible starting values, so new starting values were used. We can also take a look at the model averaged estimates. These are the estimates taking all models into account, so also the models assuming no effect and no heterogeneity. And we can see the mean estimate and for heterogeneity and the effect size, and also median estimates and confidence intervals. And the same for the model averaged weights. We can see the estimated publication probabilities in different intervals, the mean publication probabilities and the median publication probabilities, and we can also see confidence intervals here. Now let us take a look at the inference tab. Here we can look at the conditional estimates first. The conditional estimates, unlike the model averaged estimates, are those estimates that assume a parameter to be present. So the conditional estimate for effect size is based on the models that assume an effect to be present. In this case, it doesn't make a lot of a difference because all the posterior probability was for the effect size models anyway. So when averaging over the non-effect size models, they got such a little small weight that they didn't really influence the mean estimate. However, for the conditional weights, we can see that the publication probabilities are now lower. And the reason for this is that the model averaged weights took the models that assume no publication bias into account. And so, of course, the publication probabilities are higher when including these models. Let us now take a look at the Models Overview tab. Here we can see a table which gives the posterior probability and the inclusion base factors for each individual model. So for example, spike 0, spike 0, spike 1 is a model assuming no effect, no heterogeneity, and no publication bias. And in this way, there are 12 different models. You can see the evidence and the posterior probability of each of them. We can also look at individual models. However, this is not always needed after inspecting the models overview. So let us now take a look at the plots. First, we have forest plots of the observed effects. This is just the meta-analytical forest plots of observed effect sizes. And we can also see that we can see here study 1 to study 18, which is maybe not ideal. So we track the study label into the study labels box. And then the forest plot will appear with the study names on the left side. We also have estimated effects and BOSS. Let's tap BOSS. And now we will see the observed effect and the estimated effect in gray below. We can basically see that the estimated effects shrink towards the pooled mean, as is usually the case in meta-analysis. We can also look at prior and posterior plots. Let us do this for an effect. Here we can see the prior and posterior for the effect size. So the prior was null spike 0 and the alternative normal distribution on the Collins D scale. And after updating on the data, we can see that most of the probability mass is not around 0. So there's strong evidence against 0. And the mean is around 0.24 as a C model averaged estimate. We can also have similar plots for heterogeneity and for the weights. We can also look at the individual models estimates. So let's, for example, look at the individual models assuming an effect. And then we can see all models assuming an effect and their effect size estimate. So here's, for example, the model assuming an effect, no heterogeneity and no publication bias. and this would be the model assuming an effect, no heterogeneity, but assuming publication bias. And we can see the estimate for each of the 6 models assuming an effect. Finally, before closing, we should also check the MCMC diagnostics. To do so, we click MCMC diagnostics and then overview, and a table with MCMC diagnostics will appear. Here, it is most important to check that the maximum airhead is below 1.05, so this looks all good here, and the minimum effective samples are above 500, this also looks good. This concludes the video on robust Bayesian meta-analysis with default priors, and looking forward to talking to you in the video on specifying custom priors.